Welcome to Omni Eyes, where we explore the hidden wonders of nature and the incredible science behind them every single day. Today we dive into the fascinating world of the kingfisher, a bird with visual capabilities that rival our modern optical engineering. Watch this magnificent creature perform a breathtaking dive right into the rushing river, perfectly targeting a tiny fish below the surface. Have you ever wondered how this amazing bird can see clearly through the air and then instantly focus underwater without blurring? Human eyes are completely useless underwater because the density of liquid bends incoming light in a way our lenses cannot handle. When we open our eyes beneath the waves, everything appears blurry and distorted, making it impossible to hunt for small prey. But the kingfisher has evolved a magical biological solution to this complex optical problem, allowing it to become an ultimate predator. Inside the tiny skull of this colorful bird lies a sophisticated visual system that scientists refer to as a dual focus. To understand this incredible mechanism, we must first look deep inside the anatomical structure of the avian eye and its retina. Most animals, including humans, possess only one fovea, which is the specific area of the retina responsible for sharp central vision. However, the kingfisher breaks all the standard rules of biology by possessing two distinct foveae within a single complex eyeball structure. This remarkable evolutionary adaptation essentially provides the bird with two different lenses operating simultaneously within the exact same small physical space. The primary fovea is located toward the center of the retina and is perfectly optimized for scanning the environment and air. While perched on a high branch, the bird uses this primary focus point to scan the water surface for any movement. This central fovea gives the kingfisher incredible binocular vision, allowing it to judge distances with absolute precision from far away above. Once a fish is spotted, the kingfisher launches itself from the branch, tucking its wings to accelerate like a tiny missile. During this rapid descent through the air, the primary fovea remains locked onto the target, constantly updating the exact trajectory required. The bird calculates the refraction angle of the water surface, adjusting its dive path to account for the bending of light. Then comes the critical moment of impact, where the bird breaks the surface tension and enters an entirely different optical medium. In a fraction of a second, the visual environment changes drastically, and the primary fovea suddenly becomes completely useless and blind. This is exactly where the magnificent secondary fovea activates, taking over the visual processing duties the moment water touches the eyes. Located near the edge of the retina, this secondary focus point is specifically shaped to correct the extreme refraction of water. The lens of the eye does not physically move or change shape during this rapid transition between the two different mediums. Instead, the bird simply switches its active neural pathway from the central fovea directly to the secondary fovea in an instant. Imagine having two entirely different cameras built into your head, and you can switch between them without pushing a single button. This biological marvel allows the kingfisher to maintain absolute visual clarity as it plunges deeper into the dark and murky river. The secondary fovea acts incredibly similar to a wide-angle lens, providing a broader field of view in the underwater environment. This wider perspective is absolutely crucial because the fish might dart away suddenly when it detects the splash of the bird. With its underwater vision perfectly engaged, the kingfisher tracks the fleeing prey effortlessly, adjusting its final strike with deadly surgical precision. The sharp beak snaps shut around the silverfish, securing the hard-earned meal before the bird begins its upward ascent. Breaking the surface once again, the visual process reverses instantly, switching back to the primary fovea for clear navigation in air. The bird flies back to its high perch, shaking off the water droplets while enjoying the successful outcome of its hunt. Scientists and engineers have spent decades studying this exact phenomenon, trying to replicate the elegant efficiency of the avian visual system. In our modern world of technology, we carry a somewhat similar concept right inside the small rectangular smartphones in our pockets. When you open your camera application, you can easily switch between a telephoto lens and a wide-angle lens for photography. The telephoto lens helps you capture distant subjects clearly, much like the primary fovea of the kingfisher scanning from a branch. Meanwhile, the wide-angle lens captures a broader scene, mimicking the secondary fovea used by the bird during its underwater pursuit. However, our highly advanced smartphones require multiple physical lenses and complex electronic sensors placed side by side to achieve this effect. The kingfisher accomplishes this exact same dual lens functionality using only a single biological eyeball that is smaller than a marble. This level of extreme miniaturization and instant optical switching is widely considered the ultimate holy grail of modern optical engineering research. Imagine a future where artificial cameras can shift their focal length instantly, without any physical moving parts or bulky external attachments. Such a revolutionary breakthrough could completely transform medical imaging devices, making endoscopic cameras much smaller and significantly more capable during surgeries. It could also enhance autonomous vehicles, allowing their visual sensors to adapt immediately when driving from bright sunlight into heavy rain. The secret lies in the asymmetrical shape of the kingfisher eye, which naturally creates two distinct optical pathways for incoming light. Light passing through the center of the pupil hits the primary fovea, delivering a sharp and highly magnified image of reality. But light entering from sharp angles is directed toward the secondary fovea, which processes the distorted underwater images into clear pictures. Furthermore, the retina of this bird is packed with a massive density of specialized photoreceptor cells that detect microscopic color variations. These specialized cells contain tiny droplets of colored oil that act as microscopic filters, enhancing contrast and cutting through surface glare. This natural polarization filter allows the bird to see directly through the reflective surface of the water without being blinded temporarily. It is like wearing a pair of high-quality polarized sunglasses that are permanently integrated into the cellular structure of eyes. Every single dive is a masterclass in physics and biology working together in perfect harmony to ensure the survival of species. The brain of the kingfisher must also be incredibly fast to process this sudden switch in visual input without any lag. In human terms, it would be like suddenly swapping your brain visual cortex with another one in a fraction of milliseconds. The neural pathways connecting the eyes to the brain are optimized for this rapid data transfer, preventing any dangerous sensory overload. If a human experienced this sudden optical shift, we would likely suffer from severe dizziness and complete loss of spatial awareness. But the kingfisher navigates this extreme sensory transition with elegant grace, maintaining its deadly focus on the target without any hesitation. Let us slow down the footage and observe this magnificent biological process step by step to truly appreciate its complex beauty. Here the bird sits patiently on the branch, its primary fovea locked onto a faint shadow moving beneath the rippling water. The muscular tension builds in its legs as it prepares for the explosive leap that will send it hurtling downward fast. As it leaves the branch, gravity takes over, and the bird becomes a streamlined projectile designed for maximum aerodynamic flight efficiency. The wind rushes past its feathers, but its head remains perfectly stabilized, acting like a biological gimbal tracking the moving prey. The distance closes rapidly, and the bird extends its sharp beak forward, preparing to pierce the surface tension of the river. In the final millisecond before impact, a translucent protective membrane, called the nictitating membrane, slides across the eyes to prevent injury. This built-in safety goggle protects the delicate cornea from the harsh impact of the water, while still allowing light through. Splash! The bird enters the water, surrounded by a chaotic explosion of silvery bubbles and swirling currents in the dark depths. The primary fovea goes dark, and the secondary fovea instantly lights up, providing a clear, wide-angle view of the underwater. The fish, startled by the sudden intrusion, attempts a desperate escape maneuver, darting toward the safety of the tangled river weeds. But the wide-angle vision of the secondary fovea easily tracks this erratic movement, allowing the bird to adjust its course. With a powerful thrust of its wings underwater, the kingfisher closes the final gap and snaps its beak around the target. The hunt is successful, and the bird immediately uses its natural buoyancy to float back toward the bright surface above it. As the head breaks the water, the nictitating membrane opens, and the primary fovea instantly regains control of the visual feed. The transition is completely seamless, allowing the bird to spot any potential aerial predators before it even takes flight once again. This continuous cycle of hunting demonstrates one of the most sophisticated visual adaptations ever discovered in the entire history of zoology. When we look at modern optical devices, we often feel a sense of pride in our advanced human engineering and technology. We build massive telescopes to peer into distant galaxies, and tiny microscopes to observe the fundamental building blocks of life itself. Yet nature has been quietly perfecting these optical technologies for millions of years through the slow and relentless process of evolution. The dual focus system of the kingfisher serves as a humbling reminder that biology often holds the answers to our problems. By studying these natural wonders, Researchers are discovering innovative ways to overcome the physical limitations of traditional glass lenses and mirrors. Liquid lenses, which can change shape using electrical currents to adjust focus instantly, are directly inspired by biological eyes like these. Perhaps one day, the cameras in our phones will no longer require multiple lenses protruding from the back of the device. Instead, they might use a single dynamic lens system that mimics the elegant dual fovea design found in the tiny kingfisher. This bio-inspired engineering could lead to cameras that are thinner than a credit card, yet more powerful than professional equipment. Beyond photography, this technology could revolutionize search and rescue drones, allowing them to scan vast oceans and dive underwater seamlessly, too. A drone equipped with a kingfisher-inspired visual system could spot a missing person from above and dive to assist immediately. The potential applications are truly limitless when we combine the brilliance of natural evolution with the precision of modern human engineering. But for now, the kingfisher remains the undisputed master of dual medium vision, reigning supreme over the rivers and the skies. Every time you see this beautiful blue and orange bird perched near a river, remember the incredible biological machinery hidden inside. It is not just a simple bird looking for a meal. It is a living marvel of advanced optical physics operating. The natural world is filled with these hidden miracles, waiting patiently for curious minds to uncover their secrets and understand them. From the microscopic structures of insect wings to the complex visual systems of hunting birds, nature is the ultimate master engineer. Our journey today has taken us from the branches of a quiet riverbank into the complex optical physics of biological lenses. We have witnessed how a single eyeball can effectively perform the demanding job of two completely different camera lenses working simultaneously. We have explored the holy grail of optics, a system that shifts focus instantly, without any physical movement of the lens. The next time you take a perfectly focused picture with your expensive smartphone, take a moment to appreciate this technological achievement. And then remember that a small, colorful bird has been doing the exact same thing effortlessly for millions of years already. Science is not just about inventing new things. It is often about discovering what nature has already perfected long before us. By observing the wild, we learn how to build better tools, create smarter technologies, and ultimately understand our own place better. The story of the kingfisher and its dual focus eyes is a perfect example of why we must protect natural habitats. When we lose any species to extinction, we do not just lose a beautiful animal. We lose profound biological engineering knowledge. Every creature holds a unique piece of the evolutionary puzzle, offering brilliant solutions to the complex challenges of survival on Earth. Thank you for joining us on this fascinating exploration into the dual focus visual system of the incredible diving kingfisher bird. We hope this journey has inspired you to look at the natural world with a renewed sense of wonder and curiosity. Be sure to subscribe and hit the notification bell so you never miss another exciting episode about the miracles of nature. Share this video with your friends and family to spread the knowledge about the amazing scientific discoveries hiding in plain sight. This has been Omni Eyes, your ultimate guide to the hidden science of nature, and we will see you next time.